Bismillahirrahmanirrahim. Assalamu alaikum ji. Let's continue our discussion on Bayesian learning. We're talking about Naive-based classifier, and we did one example in which we used Naive. In fact, we developed Naive-based classifier. So today we'll mathematically formulate this Naive-based classifier. So this Naive-based classifier belongs to a class of classifiers which we call generative classifiers. So in generative classifiers, we attempt to model class. It simply means we want to build a generative statistical model that informs us how a given class would generate the data we have. Ideally, we want to learn the joint distribution of the input x and output label y, that is probability of x comma y. This is the joint distribution of input and label. And once we have this joint distribution for a test point, generative classifiers predict which class would have most likely generated the given observation or a set of observations. So that was the principle of Bayesian learning, right? Mathematically, prediction for input x is carried out by computing the conditional probability of y given x, and then you select the most likely label y. That is maximum a posterior estimation of the label, right? But we cannot compute probability of y given x. Instead, we use the Bayes rule and compute this probability of y, right, which we call prior, and probability of x given y, which we call likelihood. This is all we discussed in the previous videos as well. So estimating prior and likelihood from the data is called generative learning. This is the principle. Okay, let's mathematically formulate Naive-based classifier. So we have this data. We had been using this notation consistently throughout the course. We assume that we have n-class classification problem. In the key idea in Naive-based classifier is that we want to estimate probability of y given x from the data using the Bayes theorem, such that we can use this map principle to obtain the most likely label, right? So we maximize, we pick the label y from the set, and we carry out this selection such that probability of y given x is maximized. In this, okay, so when you move from this step to this step, here we have used the Bayes theorem. Estimating this probability of y is easy, right? For example, if your label takes on discrete binary values, for example, coin tossing problem or a spam versus non-spam problem, we simply need to count how many times we observe each class outcome and divide by the number of the total number of points we have. That will give us an estimate of probability of y, right? But estimating likelihood function, probability of x given y, is not easy. Why? To illustrate this, consider an example in which we take m is equal to 2. M is equal to 2 means we only have 2 labels. It's a binary classification problem. And we take d is equal to 6. That means we have 6 number of features, and we're assuming that we have binary features. As an example, assume that we have data something like this. So all of the 6 features are binary. Output is also a binary variable. Okay. This could be something and data coming from some on-off sensors. You have 6 sensors on a machine, and you're getting data from those sensors every 5 minutes. So getting at 7:50, 7:55 p.m. and 8 p.m. and so on and so forth. Right. So given this data, we want to estimate probability of x given y, likelihood function. Right. This is equivalent to, given y, we want to estimate this joint probability. If we assume for a binary case, how many parameters do we need to fully estimate probability of x given y? because we want to compute a joint probability, we need to compute all 2 to the power 6 outcomes. If in non-binary case, this number will explode exponentially, right? So we need to represent these many outcomes or probabilities for each y. And if I generalize this for d binary features, we need to represent all 2 raised to the power d outcomes. Learning the values for full conditional probability would require enormous amounts of data because we want to compute these many probabilities, 2 raised to the power d. To overcome this problem, we make a naive assumption, which we did last time as well, right? If you recall the previous example. So what was the assumption did we take? Right? And we call that assumption as naive assumption. And that naive assumption is, we assume that the features are mutually independent given the label. And with this assumption, what is the consequence? The joint probability of x given y, probability of x1, x2, xd given y can be written as a product of d number of individual probabilities, right? How many probabilities now we need to compute? So for each feature and for each label, 1 probability. If we have d number of features and you have 2 labels, if we assume it's a binary problem, then we need 1 for each feature label and consequently 2 times d probabilities. Obviously, if you have m labels, this would correspond to m times d. What is the interpretation of this naive assumption? So let me show you one interpretation graphically, that how do we interpret this computation of joint probability by exploiting or by assuming that the features are independent. Consider this example, so which I've taken from these lecture notes. We have this original data. We have 2-dimensional problem. The feature space is 2-dimensional, and we have 2 labels, right? So we have y is equal to 2 here, and we have y is equal to 1 here. So given this data, we want to estimate the joint probability distribution of x1, x2 given y is equal to 1, and we want to compute x1, x2 given y is equal to 2, right? Okay. With this naive assumption, we assume that the features are independent. It simply means you first compute the estimation along the first dimension, right? So you only compute the distribution, the likelihood along y-axis, right? So this red is the distribution for when we have probability of x1 given y is equal to 2, and here we have probability of x1 given y is equal to 1. And then we carry out the estimation along second dimension, right? So this is probability of x second feature given y is equal to 2, probability of x2 second feature given y is equal to 1. And then we simply multiply these 2 density functions or these 2 distributions to obtain this joint distribution, which is assuming that the features are independent, right? Before we move forward, we ask a simple question here. Is this assumption realistic? Do we actually have features independent of each other? This is a very, very strong assumption. So this is not true in practice, but we see that with this, even with this assumption, when we develop classifiers, we get a very, very good accuracy. We can design a very good classifier with this assumption. For example, a setting where the Naive-based classifier is often used as spam filtering. Here the data is emails and the label is spam or not spam. This Naive-based assumption implies that the words in an email are conditionally independent. Given that you know that an email is a spam or not, clearly this is not true. Neither the words of spam or not spam emails are drawn independently at random. However, we see that the resulting classifiers work well in practice, even if this assumption is violated. Right? Okay, once we have computed these likelihood or these conditional probabilities, we can use the Bayes theorem and simply we can invoke the map rule to find out or to finally come up with a naive Bayes classifier, right? So we have computed this product of probabilities, likelihood function. This is prior, and we compute this for each y, and we select a y in the class y for which this product likelihood times prior is maximized. Okay? And this is our simple naive Bayes classifier. It simply requires the computation of these likelihood function and prior, or these probabilities for each feature and for each label given the data. In practice, instead of maximizing this product, as we did earlier, we maximize the log, or in fact natural log of the function. When you take log of this, we can change this product into summation, and when you further simplify, we can also write these probabilities, which are conditional, and this is from the prior. Okay, how many probabilities do we need to compute for a naive Bayes classifier? So we need 2 times d for, okay, we're assuming it's the features are binary and the label is binary. So 2 times d for conditional probabilities and only 1 probability of y. Because when you know probability of y is equal to 1, or you compute probability of y is equal to 0, you can just simply compute the other by subtracting it from 1. Right? So we only need 2d plus 1 probabilities. Right? In general, if you have d features and m labels, we compute these probabilities and store them in the form of probability tables. I will talk about this in a while. Okay, once we have this classifier, how do we train this classifier? So we assume that each feature and label as a binary variable, just to understand the concept. Hypothesis space has 2d plus 1 different binomial distributions, which we want to compute. So we want to compute probability of x ith feature given y, and probability of y for each feature and for each label. And we have d such features. Since it's a binary variable, it can take either 0 or 1. It's a Bernoulli random variable. Each probability can be parameterized by a single variable theta. Recall, when we define Bernoulli random variable, we can simply use one variable to characterize the distribution of a Bernoulli random variable. Right? Since we only need to learn one single variable theta, we treat learning of each of these as a separate MLE problem, because we have already assumed independence. We can compute each probability of xi given y for each I separately, and separately by separately solving a maximal likelihood estimation problem for each I. So, and this is an estimate of the probability given the data. Right? Okay, let me explain this. So we want to compute that ith feature is equal to j given y is equal to k. So we have a conditional probability. We know that y is equal to k. So we simply count the number of data points, number of instances in which ith feature is equal to j, and label is equal to k. And we divide by all the instances for which label is equal to k, where j and k, since it's a binary problem, they both belong to 0 or 1. Right? Similarly, we can compute probability of y is equal to k as we simply count how many instances we have in the data for which label is equal to k, and you divide by, in fact, this is n, to total number of points we have. Right? That's how we compute the likelihood distribution, likelihood probabilities, and we compute probability of y is equal to k prior. Right? And we compute these probabilities during the training stage. As we saw earlier, these probability estimates maximizes the likelihood function, right? So we are computing these estimates as by solving maximal likelihood problem for each I, right? Once we have a trained naive-based classifier, we can use it for prediction. Let's see how can we use it for prediction. We can simply employ the same map rule to develop a naive-based classifier. For any new test point x new, we compute posterior probability, which is a product of likelihood and prior probability. So we have computed all of these during the training stage. So using this information, for any new test point, we compute these product. So the product of probabilities for each y, and we choose a y for which this posterior probability or likelihood times prior is maximized, right? So, but we have a problem here. If you observe, we have a product of probabilities here, which we are computing from the data. And there is a possibility that one of the probability is 0, and the estimate of one of the probability is 0. And consequently, if any of the estimate probability is 0, the product would be 0. How do we resolve this? The solution is termed as additive smoothing or Laplace smoothing. So what is this additive smoothing? We simply add, when we estimate these probabilities, we simply add some positive L in the numerator. Okay, what is the interpretation of this addition of L? Okay, what do we have in the numerator? In numerator, we have a count of instances for which xi is equal to j and y is equal to k. If this count is equal to 0, so we don't have this representation in the data, probability would be 0. But addition of this L would not make it 0. It will be close to a very small number, but it won't be 0. Okay, how do you see this L? So previously the count is the actual count, and now what you're adding is, so for example, L is equal to 1. It simply means you have added an instance in your data for which ith feature is equal to j and label is equal to k. Right? So to balance this, right, so that the sum of all probabilities is equal to 1, we also make addition in the denominator, which is L times R. Okay, I will explain this R in a while. Similarly, when we compute the probability of y is equal to k, we also add L in the numerator and L times M in the denominator. The idea is same. If we choose L is equal to 1, here L can be any positive number, but if we choose L is equal to 1, this is referred to as, in the literature, add 1 smoothing. We are simply adding 1 in the numerator and L times R or L times M in the denominator. What is R here? R is the number of values ith feature can take. Right? there's a possibility. Okay, for binary case, R is equal to 2, but in general, R can take any values, or a feature can take any values. So R is the number of values xi can take. So simply divide by L times R in the denominator. And here M is the number of classes we have, because when we're computing probability of y is equal to k, we're using M here. So M is the number of classes, and for binary case, M is equal to 2. In the sequel, we will do one example on text data, in which we will build Naive-based classifier, and we will also carry out this add-one smoothing, and that will further strengthen your concepts. For now, we talk about some of the extensions or variations of Naive-based classifier. We assume that we have M-class classification problem, and so we generalize it. Right? We have seen a binary classification problem. Now we assume that we have M-class classification problem. And we also assume that each feature xi can take so one of li values. So number of values xi can take is given by li, right? So each feature can take different number of values. If we have this classification problem, we can learn the likelihood and prior. We can compute the probabilities in a similar fashion by simply counting. How many probability tables do we have if we have D features and M labels? So we have D number of features and we have M number of labels. So we will need D times M plus 1 probability tables. And in each table, we will have probabilities for that feature and for that value of the label. So we have a different table for each feature and each value of the table. And finally, we need one more table for the prior. So in total, we need D times M plus 1 probability tables. And the size of each table depends on the number of values xi can take. Right? Because then that would depend on the value of this li. The set of tables for a single feature for all labels is referred to as conditional probability table. So we'll have conditional probability tables for each value for a single feature, but for all labels. Right? And we have D number of conditional probability tables, because each CPT corresponds to all labels and single feature. So we have D number of features. So in total, we will have D CPT. Okay, let's talk about incorporating model parameters in the formulation. So far, we considered a binary case and assume that a single parameter characterizes probability model associated with each feature. In general, we can have parameters defining the probability model, and we learn parameters of the probability model during the learning stage. We did one example, and we saw that in that example we had binary features, and when we had binary features, we can simply use one variable theta to model my probability density function. But if the variable can take more values, or the variable follows some other distribution, we need to learn the parameters of probability model during the learning stage. And in the assignment, you will be estimating for Poisson distribution, the parameters of the Poisson distribution from the data. So during training stage, in fact, we are learning the parameters of the probability model, which we can later use to define or to compute probabilities during prediction. Right? Okay, let's talk about one more extension of Naive-based classifier, that is Gaussian Naives. in practice, some features are discrete. For example, we have gender, you're married or not, but we can have continuous features. For example, temperature or height. So these are the continuous features, or weight, right? So a variable can take values on a continuous scale, and for this, the probability model or distribution for each feature must parameterize differently. In general, or mostly, very often, when we have a continuous feature, when xi belongs to R, we use Gaussian distribution to model the probability density function of a real valued feature, or real valued, in fact, which is a random variable, right? So for a real value random variable, we use Gaussian distribution to model probability density function. And we know that this is what the PDF of a Gaussian distribution is. We simply assume that probability of xi given y is equal to k, it follows a Gaussian distribution, right? It's a likelihood function. The likelihood function follows a Gaussian distribution. If you note here, I have not indicated dependence of mu and sigma on I for a compact representation, or for notation convenience. But for each I, we will have different value of mu and different value of sigma square, because mu quantifies the mean of the distribution and sigma quantifies the spread of the distribution. Just like we have different probabilities for different discrete features, right? How do we compute this mu and sigma for each I? We assume that probability of xi given y is equal to k follows a Gaussian distribution with mean mu and sigma, and given data we want to learn mu and sigma for each I and each k. So given I, we assume that I and k are fixed. We want to compute mu and sigma as sample mean. We compute mu and sigma as sample mean and sample variance, where the sample corresponds to for which associated label y is equal to k. How do we compute sample mean and sample variance? So mathematically, we can compute sample mean using this notation. How do you interpret this? So xji, ith feature, and jth sample, jth instance of the training data. We have a summation over all training data, but we will only count those values of the feature for which label is equal to k. So yj is the label associated with the jth instance. When yj is equal to k, delta yj minus k, delta z would be 0. The argument of delta would be 0, and delta of 0 would be 1. And we'll only count the values of the feature for which label is equal to k. And you simply divide by the total number of, count y is equal to k. All those instances for which y is equal to k, for which the label is equal to k. Right? That's how you compute a sample mean. And similarly, we can extend this to compute a sample variance. Right? So you subtract mean from each value of the ith feature, and you simply sum from j is equal to 1 to n, and we'll only include those values, those data points, those instances for which the label is equal to k. Right? So, and we need to compute this for each label, and therefore we need to estimate d means and d variances. So we need to compute this for each feature, and for each label. And for each label, we need to estimate d means and d variances during the training. Okay. Okay, let's conclude. Let's summarize Naive-based classifier. In Naive-based, we compute the probabilities or parameters of the distribution, defining probabilities, and we use these to carry out predictions. Naive-based can handle missing values by ignoring the samples during probability computation, and therefore, due to this, Naive-based is robust to outliers and irrelevant features. Naive-based algorithm is very easy to implement for applications involving textual information. For example, spam filtering, or you want to carry out sentiment analysis or news article classification. Right? So Naive-based classifier is that gives you a very, very good performance for these tasks, these classification tasks. In Naive-based, convergence is much quicker as compared to logistic regression, which we'll study in the next. And that is discriminative in nature. Right? We will study logistic regression. This is our next topic. Naive-based performs well even when the independence assumption between features does not hold. And finally, the resulting decision boundaries for Naive-based can be non-linear and piecewise. And this makes Naive-based classifier very, very attractive. The downside of Naive-based classifier, it is not robust to redundant features. It is robust to irrelevant features, but it is not robust to redundant features. If you have features that have a strong correlation with each other, Naive-based is not a good choice, obviously, because the assumption does not hold. Naive-based has a high bias and low variance, and in Naive-based you don't have any parameters which you can tune. There's no regularization, and in fact there are no parameters which you can tune to adjust the bias. Okay, so we stop here. In the sequel, I will talk about one example on Naive-based classifier, and then we will start with logistic regression. Thank you, Ji.